All right, so I'm going to talk, after Walter's introductory talk, I'm going to talk about a little bit of a fringe topic, 3 unlikely successful features. And what do I mean by that? So there are features that are obviously good to have. Like, I'm sure we can enumerate some. Purity, is it good? I mean, come on, right? More purity is good, more type inference is good, more immutability is good, or less mutability if you wish. So all of these are obviously good things to have, right? Property inference, for example, you want to infer that the function is not going to throw, it's going to stop, it's going to be always successful. Automatic things like that are obviously good. So I'm not going to talk about all that. What I do want to talk to you about are unpredictably successful features. Features that we put in the language with a vision and with hope, and they turn out to be very successful. The first one would be the scope statement. A very simple statement. It's not, for example, like getting back to the obviously good features, modularity is good. Any dependency control is good to have, right? Scope is inside the function. So all of a sudden we go from the top, from the top level view, we go inside the function. We discuss what's happening there. Well, what's happening there? Inside the function, you need to do certain actions. I'm going to focus on one particular action. So for one action, I noticed very often there's a need to do some cleanup after the action. You open a socket, you want to close it later on. You open a file, you want to close it later on. You open a database connection, you want to disconnect later on, right? So there's a cleanup associated with many actions. And then there's also sort of the CPS style, if you wish, the continuation passing style. There's some stuff that you need to do after you've completed the action, but before you do the cleanup. So you open a database connection, you want to do some SQL against the connection and get some results, and then you clean up. And then there's a third thing that's very, very common. That would be sort of the rollback action. And that's what you do when the next thing failed. So you perform the action, it succeeded. You attempt the next thing, it doesn't succeed. You need to clean up in any way. You need to close the database connection, but maybe you want to, just before, with your last breath, before dying, you want to log a message that, this thing didn't quite work out. Or you want to, output to a log, you want to retreat, you want to reestablish application state and whatnot, right? So this is a very extremely generic and abstract model of evaluation, if you wish, of individual simple actions. So far, so good. Do I agree that we have what to talk about here? I see one nod. That's good. I'm going to take that as a compliment. So let's see how we do all this in several languages. Well, in C, good old C, well, let's assume action is sort of a function that returns a Boolean of sorts. So I say, well, if action, then I'm going to try the next thing. And if it fails, I'm going to do the rollback action. And then I'm going to do the cleanup. Now, notice that this is not code. So it uses all these angle brackets that are not ASCII, right? If you squint carefully, okay, you're going to notice that these are not angle brackets. So this is not real code. So I use sort of the math angle brackets to symbolize that I'm talking about abstract actions as opposed to concrete function calls and whatnot. But the shape of the code in C generally is like this. I'm sure you recognize it. I'm sure you've written it many, many times, and it's instantly recognizable. Well, in C++, the politically correct way to do sort of action and cleanup, it's RAII. The way you do, you pull the action out into a separate type, and say, well, in the constructor, I do the resource acquisition, and in the destructor, I'm going to do the resource initialization. That was testing your attention. Apparently, you're not paying attention because I'm not doing initialization in the destructor. I'm doing deinitialization. I'm doing the cleanup, right? Thank you, Shaz. One nod. Great. So here I'm going to do that little class, which is actually, so for certain resources, the action and cleanup pair very well because they have an underlying state. files, databases, right? I'm opening the file, I'm going to close the file, so they belong together very nicely. But sometimes the action is not really associated with any state. And this is very clearly, very nicely witnessed by classes that end with R, ER. Indenter, appender, doer, stuff like that. Like, for example, I want to print some trees. I want to print some printed code, some, hierarchical structure. And, whenever I enter, I want to indent by 4 spaces or whatnot. And whenever I exit, I want to de-indent by 4 spaces, right? Or HTML, I want to put a tag in the perlink closing tag. What's going to happen then is I'm going to have all these silly types that actually don't encode any meaningful state as much as pairs of actions. That aside, this has been a very successful pattern for C++. But, we're not done yet. We still need to do the rollback, in which case we need to use a try and catch statement, which looks pretty much like this. We've all written such code. Notice that very often, one of these possible actions may be empty, in which case if rollback is sort of the null action, then I don't need to write the try statement at all, so I'm home free, or almost free if I discount for the creation of a new type. All right. Now in Java and C#, things are a bit different. I don't have ready access to this RA idiom that C++ offers with its destructors, but I do have a finally statement, so I'm going to use it. And the way finally works is the cleanup is going to execute no matter what, come hell or high water, and the rollback is going to happen only if I catch an exception that's thrown by next, right? So again, we've all written code like this. Make sense? So far, so good? Okay. I'm seeing like, this guy wants our nods. All right. I'm going to nod. So, in Go, we just heard this talk about Go. In Go, there's a defer statement which makes attempts at making things a bit cleaner. Unfortunately, still fail, as we'll see soon. But in essence, you actually have an action that returns a result and an error. And then you say, well, did the error happen? If it didn't happen, I'm going to defer the cleanup down to the end of the function, not the scope. Careful there. Which is a bit of a smell that can cause some interactions. It's not the end of the scope, it's to the end of the whole function. And well, if the next, the CPS next thing to do fails, I'm going to do the rollback step. So far, so good. What's the elephant in the room? Where is it? Do you see it's patterned, right? So it's like, what's this? So this is a nice piece of art because the elephant is actually not obvious because painted in the same color as the wallpaper. So I found this piece of art very interesting. It's a contemporary piece of art. All right. What's the elephant in the room? Composition. So in the typical function, I casually do more than one action. If every function consists of one action, we'd be okay because we can do stuff like that and like that and like that, right? We can do it. We are professionals. We can sit down, write the code, and get it done, right? But getting back to the pattern elephant here, if I'm trying to compose the 2 actions, I'm not asking for much. 2 is the smallest number greater than 1, right? Integer, that is. So, I'm asking for 2 actions. So in C, you know what I did? I took and pasted the code of one action instead of next. So I got this. And do you write this? Actually, you might have seen or written even code that linearizes this. Because I've seen code in C at companies that forbid goto except if it's goto cleanup. I'm seeing the nods now that are spontaneous this time. I didn't ask for them, right? So we don't use goto, except if it's goto cleanup. Yeah, that's fine. Yeah. As you were. Carry on, okay? So people do this kind of stuff. They say, oh, I'm going to linearize this. I'm going to, pull the scope back. So whenever something bad happens, I have here, it's essentially, it's like in the war, it's a system of trenches. Because people, they do something, they dig a trench. They put a label for the go-to for the cleanup. And then they make a new assault, and they build another trench, and then they put another cleanup action, and so on. So at the end of the typical C well-intended function, you're going to see these labels with cleanup actions that nicely unroll whatever actions you manage to do. And then there's a go-to cleanup 1, go-to cleanup 2, and so on, right? So I'm confident that you've seen such code, which is actually better than this, because if I take you to the third level here, you're not going to like it, right? So one detail here that motivates people to use that idiom is that there's a small code duplication here. Rollback 1 appears twice, right? So we need to plan the code for rollback 2 times. It's kind of unpleasant, right? Okay. Well, in C++, the more classes, the merrier. So I'm going to do another class if I want to compose. And then composition is still not going to look very well if I have rollbacks in the mix. If I don't have, again, I get rid of some try statements. But that's why we're getting to a point where we need to have nested try statements. Right? This is pretty unpleasant, right? And in Java and C#, we're not better off. Actually, we're so worse off. This is kind of messing with my name. So, essentially what happens is, again, I took 2 actions. I looked at the code pattern. I did what the hell I had to do to get 2 things done or fail successfully, right? This is what it looks like. There's no other way. I mean, there are other ways. Most are incorrect, and some are based on adding state. So you have an int that says, where did I get? How far did I get in the computation of this function? Well, I got this far, so then I'm going to clean up this far. So this is going to save on try and catch statements. But, the sort of the politically correct, naive superposition looks like this. And Go is not much better because we have 2 differs here. Differ does make things a bit cleaner. But we still have to add a certain amount of flow control to roll back things in case there's a problem. By the way, you should know that this is rollback 1. I noticed this error before, after I submitted the slide, so I didn't have a chance to fix it. This is rollback 1 because I'm fixing action 1 if the second action has failed. All right. Now, clearly this is not scaling. Yes? I missed the rollback 1. If not next to, I need to do, you are right. Yes, I still need to duplicate code there. Thank you. Oh, so there's 2 bugs. All right. Well, I'm not an expert in Go, but I should have gotten this right. Thank you. Apologies about that. So yeah, I still need to insert 2 rollbacks on the next 2 case. If that next 2 fails, I need to do 2 times. Okay. So far, so approximately good. All right. So the problem here is that this location and nesting is failed. The common pattern of these pieces of code is that they take the normal path of execution, the happy case, rip it off where it was, where it belongs, which is at the left edge of the screen in Emacs. You don't use another editor, do you? Nobody should use. Okay. So you rip it off from where it belongs, and you embed it into a larger structure. Control flow, try, catch, if, else stuff, right? So rip off the code and you put it elsewhere, either in a class in the C++ case, in an if statement in a C case, in a try, catch statement with these other languages that use exceptions. So in all cases, you dislocate the code from where it belongs and you insert it, embed it in a larger structure. Years ago, I worked on a very nice program that had 1 bug. The bug was whenever a dialog window appeared, it appeared 1 pixel to the right. There's an application, people use the application, and every time the dialog appeared, whoop, 1 pixel. So it's undetectable in no testing that happened, right? Because people didn't test like 5 times and they're like, yeah, it works, whatever. And then the program got used for a month. I got calls like, I can't reach the buttons here. It's, I don't see what's going on because the damn dialogue is like off the screen, right? This is what happens here. 1 pixel is all it takes. In this case, 1 level of indentation is all it takes. You indent the thing that is not supposed to be indented, scalability goes down the drain. This is what's happening here. Dislocation and nesting, embedding in larger structures, it's going to be fail. To wit, I'm very glad and very honored that you're in Martin. This is a slide from Martin's presentation of yesterday. He presented the same code in 3 languages, C#, JavaScript, and C++. They'll have the bug. Huh? Right. So either way, each slide had the bug in different ways. That's not that's not a cheap shot at Martin, because he actually took these examples from the Microsoft technical documentation. I'm kidding. So he found some sample code and he showed it. But each example has a bug in a different way. Where's the bug? Can anyone see it? It was egregious to me. It's in red. No. No, the reds are his. It's a bitmap. So where's the bug? So we have, we have the display status connecting to whatnot. We set the display of the UI element that says request accepted to none. I'm hiding the thing. And then I have a continuation that's going to say connect the sync and whatnot. What happens here, the bug, and here, by the way, so here I'm going to hide this display element again. The bug is that nobody is going to set the display of peer finder underscore accept request to visible. The action is going to complete. The thing is never going to be visible. Nobody's doing that, right? What should happen is that at the end of the whole thing, there should be a continuation that's going to say, oh, I'm going to set the display state back to visible because I just hid it, right? And this is exactly the kind of error that you make if you don't have good mechanisms for deferring actions. To say, I'm going to write straight line code, but the sequence of execution of the code is not going to be linear. And I'm going to present a famous code, Structure and Interpretation of Computer Programs. Wonderful book. And I'm sure you've seen this code before. And somebody paraphrased that. I think the matter here is that error handling is about maintaining program invariants, and only incidentally, as a perk, is about looking at the actual error. That's that's on the side. Looking at the error is like the last thing you do rarely. Most of the time what you're worried about is keeping your program sane in the presence of errors. By the way, this famous author? Good, I made it up, right? Yes. Okay. So, this is the problem, because all code patterns that I've shown focus on the error. Where's the error? Did I catch it? Did I throw it? Where is it? Do I rethrow it? What do I do now? Right? It's all about the error. You don't look at the error. You look at the program state. You want to restore and keep the program invariant sane. That's what you want. So, enter D. In D, it's very simple because we thought the way we made it up, right? In D, the way it works is you do an action and then you schedule stuff to happen. You schedule stuff to happen. Scope failure is a statement to which you can pass any other statement. It's like an if or if you wish. You say, well, if this scope is going to be exited via failure, I want you to do this. If the third line, if scope is exited normally, in any case, scope exit, you're going to do the cleanup. And there's a rarely used variant for completion, which is scope success. And then you celebrate. There's artifice, there's fireworks, right, if you wish. So there's a, that's not very often used, but people use it sometimes, and it turns out it's there for completion. Now, how do you compose with this guy? So we have this statement. So I do action, and I say, well, if there's later on a failure, then I'm going to do this rollback. And if if later on I'm going to exit the scope via any other means, absolutely any means, then I'm going to do the cleanup. How do you compose with this guy? Right? That's what I do. I do what I do, what I do. This is it. You want more? I mean, this is it. And to wit, I hate these things that look great in demos, but are kind of just weird. Actually, so when we first came with the scope statement, the community was like, huh? What do you mean there? So with time, I did a poll on the news group before starting working on this talk. I was like, what's your favorite? And people were like, scope is good, scope is good. Why is scope good? That's why it's good. You don't need to read this, right? This is a routine that takes a file and reads it into a string. It's a bit more complicated than it should. It's a base library. It's a core library routine. Opens a file, reads it into a string, closes the file. Now here's the complication. Again, you don't need to look at the code. I want you to squint and kind of look at the shape of the code and the size of it. So what gets confusing here is that on the operating system that shall not be named, right, Unix, what happens is there are files that have size 0 but actually are not empty. It's just idiosyncrasy of Unix. So I think in var, there are some files that you open a file, you query the file, it has size 0, but if you open it and start reading, it just has data in it, and you don't know how much. So with that complication in mind, there's this reallocation of buffers, and I want to allocate an initial buffer guess, and then I'm going to reallocate if needed. But if the file did have initial size, I'm going to know exactly how much I need to read from it, so I'm good to go. So all of that logic is caught in here. This is the old routine, written in a sort of classic D without scope. It's got 3 scopes. It's written by Walter, and then I sort of introduced the obvious things in it. So it does have a little scopes in it. I'm sort of surprised if you saw them. You weren't supposed to see it, right? It does have the obvious scopes. It would have been a bit bigger even if it had absolutely no scopes. So it has a couple. This has 6 scope statements. It's more than 2 times smaller. It uses 5. So this guy has 6 levels of indentation. And the deepest level of indentation is right there. So in the middle of things, if you squint at the shape, you're going to see the tip of the arrow is at the delete buff. Right? That's sort of the failure point.
I see 2 scopes on the right.
2 scopes on the right and 3 on the left?
Yeah.
No, there's got to be more here. Scope failure, scope exit. What's happening here?
It's awesome.
No. So
Font's not small enough.
yeah, font size is too big. So actually, I remember. So the copy here is already a fairly recent version, which I then rewrote. But the main merit here is still in the scope statement because it allowed me to think about flow in a very different manner. If you look at it, you're going to see that this guy has, as its only control flow, it has a for statement. This is about it. And then everything else flows. There's absolutely no other need to do any flow control. Whereas this other function has much more flow statement because it needs to sort of manually handle all of these cases and all of these situations and restore invariants, such as delete buff up there and stuff like that. So there is truth in advertising, and people do report that after they start using this style of programming, their code becomes smaller. And here's the thing. The bigger function is written in a smaller language. Small is, you know what small? A Yugo. Small is not, huh? A Yugo, a car, the Trabant, like a crappy car can be small, and it's not a merit. You're not looking for small. You're looking for torque. You want power per weight, right? You want power divided by the size and the weight and whatnot, right? What you want is essentially you want to have a language that's small in consideration, in comparison to its power. That's what you're looking. Don't for small or big. This language is big. Okay, it's big, but it doesn't do anything. Okay, that's a bad language. This language is small. It also doesn't do anything. Is that any better? Right? So we're looking for not necessarily small as much as powerful. And actually, scope has turned out to be extremely redeeming in terms of being able to write correct code casually. And when I say casually, I'm saying without contortions. It's very easy to write correct code in D. All right. So again, my point here was it's the code that you write. So be aware that sometimes the feature for language's simplicity's sake is going to be removed from the language, kept out of the language. Not gonna we're not gonna do macros, for example, and stuff like that. But sometimes that actually you end up paying for it when you code in that language. All right. So straight line code plus implicit flow, that's a win. And this concludes my first surprisingly successful feature. It's a very small feature. Actually, it's implemented by rewrites. So if you look at these guys, they rewrite into these guys. But it's code that you don't want to write. It's exactly like, there's this great presentation on C# on a weight. And, you could do it by hand. You never want to. You absolutely don't want to. So the compiler does a great job for you at rewriting, essentially lowering high-level code for you into a lower-level C#. And then, you get a lot of benefits in your code. All right. Number 2, I'm going to talk about built-in arrays in D, which, I don't find extremely revolutionary, but they're so damn successful, I got to talk about them. They got to be here. They were actually much more successful than we ever expected. We thought they're going to be okay. They did spectacularly well. So, forget the native versus, versus immigrant language, right? Forget about that. What's a systems level language? What is a systems level language? How do you define a systems? I need a systems level language here because, yes? I need pointers. Right, so in essence, at the end of the day, you can write always a native compiler for a non-native, for a managed language, right? You can always write it because it's easy and it's not a difficult language. But it's much more difficult to write a sort of a JIT or virtual machine for a native language exactly because of those pesky pointers that stay in the way. You have all this spinning, in JNI and in C# you have what's the statement in C# like pin? Fixed, right? So you got all the fixing and all that stuff, and the compiler must track everything. There's limitations and there's trouble and there's leaks and whatnot. All because of these pesky pointers are a very low level model of memory. Actually, it's too low level because you can't increment a pointer safely, ever. You can't, because the pointer itself has no information about where it's going. You can't do any arithmetic on the pointer, ever. You can dereference it assuming you have a garbage collected language, or you can prove by whatever other means that the data is there, right? You can dereference it, so, granted. But arithmetic is impossible because the pointer doesn't know its bounds, doesn't know where it's going. What do you usually do? Use the pointer and the length. So yeah, there's pointer and there's length. And the pointer can go up to the length, but not more. Or I have a pair of pointers, and they can go, they can go until they meet, but not beyond, right? So one pointer is a pretty poor device for handling memory, especially when I talk about arithmetic. So what Walter did in D was quite interesting. He said, you know what, if one pointer is good, efficient, then two should be even better, just as efficient and with additional desirable properties. Thank you. Well, a built-in array in D is a pair of pointers. I'm lying. It's a pointer and a length, but in concept, you can't distinguish between the two. And what the two, you notice there's a hashed area there, right? You know what that is? That's not a hash table. So the hashed area there is verboten, right? It's forbidden area. You can't go there. It could be undefined to go there. So whenever you have one of these D built-in arrays, you're guaranteed to be able to explore between these two limits, but not outside. Which is a very interesting property, because now I can say, well, I have arrays and I have stuff, and I can actually, let me actually reduce the range I'm looking at in B. Do this assignment, B equals B from 1 to length minus 1, and I reduce my array of iteration. This is great for iteration, and it's safe. This is the point. It's all safe now. We're in safe territory. And the great thing about using built-in arrays that are actually pairs of pointers with well-defined limits and well-defined range is that we can now use built-in arrays in safe parts of the language because they have provable properties. As long as you have the garbage collection in the mix, you're guaranteed to be able to prove things about what's going on with a built-in array in the yes.
There's one place in which one pointer is better than two pointers. That's you want to update it, right?
There's one place where one pointer is better than 2 pointers, and that's atomicity. That is correct, and you can still actually have one pointer in D if you wish. That code is not always provably safe. But atomicity would be a long discussion nevertheless. So that would be would sort of transgress. But the enabling factor here in built-in arrays in D is that you get to have these built-in arrays that are actually safe, provable, checkable, with known bounds that you can actually use in safe code, and you can have safe code, play with them, and the compiler looks at it and says, okay. This is huge. Because in C++, it does have a safe subset. It's an unusable subset. The problem is, if you want to do any polymorphism in C++, you're stuck with pointers. And once you have the pointer, you can't do anything. The compiler cannot prove anything. All right. So one interesting rule about these built-in arrays is that they can always decrease but never increase. You can increase them by appending with an operator, but by default, you can't just take with your hand. You can't take these arrows and move them outside the range. So arrays in there are always shrinking, which is interesting because this is exactly how iteration should be going. I'm going to make progress iterating, so I'm going to iterate from a larger range to a smaller range. To wit is a palindrome, is this palindrome function, and I'm really sorry, it does use mutation. Nevertheless, it's pure because, as Walter explained, a function can change its own private state in D and still be pure. I didn't worry about annotating it as such. So, for as long as the length is greater than 1, I'm going to reduce A from both sides, and if the two limits of the range are not equal, I'm going to return false. Otherwise, if I make it to the array of size 1, then I'm done. Right?
Dollar the index of the last element?
Dollar is the length of the whole array. So that's why I need -1 to refer to the last element.
So hang on a second. If you go from 1 to length -1, doesn't that only take away from the left?
If I go from 1 to length minus 1, doesn't it always take from the left? The convention is this, just like in C++, the right side, the right edge is sort of, open, right?
Dot dot is least index, max index.
Right. So to repeat the question, so A of 1 to W minus 1 is actually reducing from both sides. On one side I have 0 based, and on the other is length minus 1, which is sort of the C++ tradition, open to the left or open to the right range. Okay. Well, the beauty here is that these built-in arrays, as simple as puny as they are, they have an enormous generalization. So Stepanov did a great piece of work with saying, you know what, I'm going to generalize what a pointer is, and he came with the notion of an iterator, which is pervasive in C++ and extremely successful. All right, so it's like the rule of 3. So if pointers go to iterators, arrays go to where? Well, all of a sudden we discovered there's this notion of a range, which is extremely general and is absolutely pervasive in D. And a range, in general, you can access the first element, like the one in this example. You may be able to access the last element if it's a bidirectional range. And you may be able to access a random element if it's on a random access range. And the generalization of the function palindrome is extremely simple because I say, well, is my range empty? And the progress I'm making is I'm popping the front and I'm popping the back of the range. And if the front is different from back, I return false. Last but definitely not least, I'm going to talk about what Walter very casually mentioned. So Walter was like, North Korea built the atomic bomb. No problem. And it was huge. It was huge news. All right? This is, whoa, what was, I want to know about that, okay? So Walter was too casual about it. I'm happy to be able to emphasize it. So compile time evaluation and mixin, it's an absolute dynamite pair. So there's been a lot of talk about embedded DSLs and about introspection and about things like macros. Right? Very often, the embedded DSLs, which I'm going to focus on, are sort of, they're forced into the host language syntax. So we've seen a DSL for parallel computation, which use Ruby as a host. So essentially, you look at it, it's just Ruby. So you have the diagrams and everything, but that's not the code. You look at the code, it's okay, that's Ruby. And then you have the DSLs for parallel computation and graph and machine learning and whatnot, all of which somehow look like Scala, no matter what you did. So that reminds me of my discussions, like, I'm with my Romanian friends, and we're in polite company. There's some native English speakers who don't speak Romanian, so we're sitting there speaking English. But when Romanians speak English, what happens is they let loose of the accent a bit. They let loose, and at some point, my English friend says, you know what, Andrei, go on, speak Romanian, because it sounds to me like Romanian anyway. So it's the same with these DSLs. No matter how ingeniously they're done, they look a lot like their host language. It's just Ruby, or it's just Scala, or it's just C++. Where are you, Eric? So for personal safety reasons, I don't have examples from Eric's regular expression syntax, which is embedded in C++. All right. But there's plenty of embedded DSLs that you actually want to have. Printing, regular expressions, EBNF, grammars, pegs, which is another form of grammar, more recent and sort of in vogue. SQL, we have a lot of embedded grammars that I don't want to write SQL with squiggles and arrows and stuff that's not in SQL. I know SQL, I want to write SQL. And it's just whatever you order, you're going to get pasta for everyone. I want a soup, I want a cake, I want, whatnot. You're going to get pasta, you're going to like it. That's how it works. Yes?
Is pasta a managed language or a native language?
Pasta is managed or... All right. Here we're going to use with native grammar, we're going to process during compilation, we're going to generate D. This is a complete grammar for expressions. This is the A-bomb. All right? This is the A-bomb. And what it does is, it uses mixin and it calls a function against the constant string. The constant string uses a free form that is PEG, actually. It's portable parser expression grammar, which has nothing to do with D. It uses the squiggle here, it uses the arrow here, it uses like, its own less than whatever, it uses like an arrow. It has its own notation which comes from the parser expression grammar literature. It's identical. And this implements multiplications and additions. Just a sec. What this is going to do, the grammar function is going to be called during compilation against the string. It's going to do string processing exactly as lex and yak do. And the mixing statement is going to take that string that's returned by the grammar and is going to explode it into decode, which is going to be passed back to the compiler. Guess what? You're going to get a parser this way. And the details of how it works, if you say enum s equals string expression is going to be evaluated during compilation because enum must be known during compilation. And if I say mix in against the string expression, I get the string passed to the compiler to get compiled immediately. And that's how the circle closes. I can compute strings during compilation and I can explode them back into decode, pass them back to the compiler is going to use them. That's how the circle closes. One sec. How you use it. And here it gets a bit confusing. You can use the generated grammar itself during compilation or at runtime. How does that work? You see what I'm saying? So you can actually say, I'm going to use the grammar right now during compilation, even though it was generated during compilation, and obtain a tree during compilation with which I'm playing during compilation. Or I can read a string from standard input and parse it. Shaz.
So I was wondering how expressive is this thing that you put inside the mixing? Can you make the compiler loop?
Can you make the compiler loop? Let me see.
Like non-termination.
Yes, you can have compilations that don't terminate. It's Turing complete. You can create objects, you can create arrays, you can concatenate arrays. All of safed is supposed to be available. There are some limits to the implementation right now, but all of safed, you can't do void star and casts, right, for understandable reasons. And you can't read files, but you can do a lot. To wit, it scales up. 1,000 lines of D grammar expressed as a grammar. It's not expressed in D. It's expressed with grammar notation. It explodes into a 3,000 line parser. So you can think of it as a highly integrated lex and yak combination, except you have the grammar, you can use it, and then you can actually use it during compilation. The result of the result of lex and yak, you can use it during compilation, or you can actually pass it to standard input and read strings and compile things. This is so powerful, I'm speechless. I don't know how to explain it. Because, when the guy came with this kind of stuff, I was like, let me think for a minute here, even though I was supposed to be an expert in this kind of stuff. I was supposed to know it. So think of it as a highly integrated lex and yak. Last thing, thank you, Mads. How about regular expressions? First line, R1 gets a regex from a string, and that's going to be evaluated, parsed, and understood, and an automaton is going to be generated during runtime. The second is an enum, so it's going to force execution during compilation, compile time regex, and it's going to do the whole machine automaton is going to be generated during compilation, is going to be actually used. Which one do you think is faster? The compile time is supposed to be faster because it has the luxury of doing analysis and everything during compile time and specialization and everything, and then the code is going to be generated specialized for that particular regex. Perl does the same trick actually, but in other ways. How much faster? Faster than the fastest in the world. This is the DNA regex shootout. It's one benchmark for regular expression engines. So everything else is in the noise. It's below Java 7. So all regular expression engines you've heard of are here, right? In the noise. Okay? I've seen like numbers like you wait for 5 minutes, and it's supposed to be complete in like 5 seconds. So have Java 7, you have Eric Niebler's expressive, which is quite a feat. You have the D runtime regex. We have RE2, which is a high-performance regular expression engine. You have the V8, which a lot of work has gone into it. The Google V8 regular expression is very good, but not as good as what you can do if you specialize during compilation. We do 1.3x that. To summarize, we discussed the scope statement, small, incredibly effective for writing correct code casually. Then we discussed a bit the built-in arrays, which are safe pointers. And finally, we discussed a bit compile time evaluation and mixin. With this, well, the conference is ending, but I think we have minus 2 minutes for a couple of questions. Thanks, Mads.
Yeah.
Thank you. All right, so there's a question earlier from back then on which
I'll take -3 questions.
Thank you.
Really just a small one. I was wondering if you embed DSLs as quoted strings, what do you do if they need quotes?
Oh, if you embed DSS as quoted strings, what do you need if you do quotes? This is a solved problem in sort of the quoting string community out there, which is like Unix shells and everything. So there's the straight quotes. You can have R quote, which is raw quote, and then you have Q. You can say Q and you open a brace and that's another quote. And finally have the back tick, which looks like a piece of lint there on your monitor, and that would be another quote. So you can combine, you can escape. So there's plenty of it's a non-issue. Yes. Okay, so don't tell me there's no more questions because.
Come on.
Yes.
Does the runtime or the standard library actually include any Lex or Yak features?
Does the standard library include any Lex or Yak features? I'm extremely aggressive about it. The work I've showed belongs to Philippe Sigaud, who agreed to submit his wonderful grammar, the parser generator library to the standard library. This is work in progress. So we're getting there. The regular expression is state of the art, is done, and it's present in the language as of right now. Last question. Yes. 2 more questions. Last 2 questions. -2.
Are there limits where in the grammar a mixin can appear, or can they appear like anywhere between any 2 tokens?
Are the limits of where a mixin can appear? Excellent. I'm sort of glad you asked that. It's a subtle matter. Mixin must be either a statement, declaration, or an expression. It can be a fragment of an expression. So you can't say mixin and say A+, and that's not going to work. It's got to be a complete expression or a complete declaration, and the compiler detects from the instantiation location. It's going to detect which is which. But yeah, so this is a subtlety. And very last question.
With respect to the scope feature, it sounds like a lot of what it offers is very similar to what scope guard classes offer in C++. Is there anything in addition to what those can offer that it provides? Yeah, so scope guard is a very old piece of code that I wrote like in 2003 with Petru Mărginean, and it's been extremely successful in C++. And there's a C++11 iteration of it with Landas, which is much more efficient. After working, so we have that at Facebook. Probably we're going to open source it at some point. So scope guard in C++ is painfully close to being useful, because the pain point there is that it can do cleanup, but it cannot detect whether the current scope is exited via an exception. It's unable to detect that for reasons, unquote exception and all that story C++ didn't quite get right. And because of that little, fly in the ointment, we couldn't make scope guard in C++ be as good as in D.
All right, well, thanks a lot.
Thank you, folks.